Hey everyone, thanks for tuning in to another episode of Fascinating Frontiers. I'm Patrick, coming to you from a drizzly Vancouver morning, and I'm genuinely excited to dig into what the universe has been up to lately. The cosmos never really takes a day off, does it? From the frozen building blocks of new worlds hidden inside vast interstellar clouds, all the way to fresh steps in human exploration and some fascinating organizational shifts here on Earth, there's a lot to unpack. Let's dive right in. One of the stories that's been on my mind all week is the incredible first light science coming out of NASA's SPHEREx mission. This little spacecraft has just delivered an astonishingly wide survey of frozen molecules locked inside the dense clouds that dot our Milky Way. By scanning across more than 600 light years of these giant molecular clouds, it has shown exactly where water ice, carbon dioxide ice, ammonia ice, and other simple ices tend to congregate long before gravity collapses them into new stars and planetary systems. The data comes from precise infrared spectroscopy that can distinguish the unique light signatures these ices absorb even when they're hidden behind thick curtains of dust that would completely block visible light. What makes this so special is that it gives us the first true galactic scale inventory linking the raw materials drifting between the stars to the water we drink every day, the comets and asteroids we study up close, and the planetary atmospheres we hope to explore with future telescopes. Astronomers now have a much clearer picture of how ice-rich material eventually ends up incorporated into the worlds forming around distant suns. To me, it feels like a beautiful bridge between the cold chemistry happening in deep space and the very ingredients that built our own solar system 4.5 billion years ago. I keep thinking about how every glass of water we drink contains molecules that probably formed in clouds just like these, maybe even in a completely different part of the galaxy before our sun was born. It's the kind of quiet, profound connection that makes astronomy feel so personal. While SPHEREx is showing us the ancient frozen raw materials that build worlds, a very different kind of milestone just wrapped up much closer to home. The crewed Artemis 2 flight around the moon has safely concluded, and I still get a bit of a chill thinking about it. 4 astronauts completed a journey that marks NASA's return to crewed lunar exploration after more than 50 years of waiting since the end of Apollo. The mission is already inspiring a whole new generation of astronomers, engineers, and space explorers who followed every moment from classrooms, living rooms, and observatories around the world. Beyond the inspiration, the data gathered during the flight is now being carefully analyzed to refine hardware, procedures, flight rules, and planning for what will eventually become a sustained human presence on and around the moon. Engineers are applying these hard-won insights directly to the designs and operations concepts that will one day carry us onward to Mars. It really does feel like a genuine turning point, the kind that shifts how an entire generation thinks about our place beyond Earth. After decades of low Earth orbit operations, we're finally stepping back out into the wider solar system again. With Artemis 2 now officially in the history books, the entire space community is already looking ahead at what comes next, and the pace is picking up. Space agencies around the world are now charting the next phases, including concepts for long-term lunar bases, resource utilization demonstrations, and increasingly clear pathways toward crewed missions to Mars. The success of Artemis 2 is opening doors for deeper international collaboration on everything from life support technology to deep space communications and operations protocols. Lessons learned about how humans and machines perform together far from Earth are already shaping the next generation of hardware that must operate reliably for months or years with limited resupply. Sustained presence on the moon will serve as a crucial testbed for habitats, power systems, radiation shielding, and in situ resource utilization before we commit to the much longer and riskier voyages farther out. What feels different this time is the focus on building lasting capability rather than chasing a series of one-off spectacular flights. It's exciting to watch an actual roadmap take shape in real time instead of remaining a set of PowerPoint slides. That momentum has me genuinely optimistic about the next decade. Speaking of technologies that could reshape those longer journeys, One idea that keeps gaining serious traction is the use of nuclear power for propulsion. Proposals for nuclear thermal rockets and even nuclear electric concepts are receiving renewed attention from both engineers and mission planners at NASA and in industry. The technology could dramatically shorten travel times for both crewed missions to Mars and ambitious robotic trips to the outer solar system. Faster transit would reduce the radiation exposure and psychological strain astronauts would face during the long coast to the Red Planet and back. It would also let robotic probes reach the ice giants or the distant Kuiper Belt in a fraction of the time they take with today's chemical propulsion. Suddenly, ambitious exploration campaigns that once seemed like century-long projects start to feel within reach when you're not spending years simply coasting through empty space. The engineering challenges around safety, reactor design, regulatory approval, and public perception are still significant, but the potential payoff could fundamentally reshape how we think about travel across the solar system. I'm really curious to see which concepts move from paper studies into actual test hardware over the next few years. While we debate those future propulsion systems, one piece of living history is still very much with us and sharing his experiences. Apollo 13 astronaut Fred Hazy will be joining a free online panel tomorrow morning at 8 o'clock Pacific time as part of the Space Education Summit. For students and space enthusiasts, this is a rare chance to hear firsthand stories from someone who actually flew to the vicinity of the moon during one of the most dramatic missions in spaceflight history. Hazy's perspective on handling the unexpected, staying calm under pressure, and working through cascading system failures will resonate with anyone who has followed that mission in detail. It continues the long and wonderful tradition of Apollo-era astronauts generously passing on their hard-earned wisdom to inspire the next wave of explorers and scientists. Events like this remind me that real human experience, told in someone's own words, is still one of the best ways to transmit the wonder, the humility, and the sheer grit of spaceflight. If you have any interest at all in the moon or deep space exploration, I hope you can carve out some time to tune in. These opportunities don't last forever. From one generation of spacefarers handing off their stories to the instruments that are mapping the entire observable universe, let's talk about an extraordinary cosmic survey that just reached a major milestone. The Dark Energy Spectroscopic Instrument, or DESI, has finished its main survey, producing an unprecedented three-dimensional map of the large-scale structure in the universe. This detailed survey provides an astonishingly rich view of how galaxies and galaxy clusters are arranged across billions of light-years, revealing the subtle fingerprints left behind by dark energy and the cosmic web of matter. The project is now extending its observations beyond the original planned duration because the data has turned out to be even richer and more scientifically valuable than anyone anticipated. Astronomers will be mining this enormous data set for years to come as they test and refine our theories about dark energy, the expansion history of the universe, and how cosmic structure grew over time. It's one of those quiet but genuinely profound moments where our map of the cosmos suddenly becomes dramatically more complete and detailed. The sheer scale of what DESI has captured is humbling when you stop to think about it. Hundreds of millions of galaxies, each one an island of stars, all woven into patterns that stretch across distances that defy easy comprehension. While DESI is mapping the very largest scales of the universe, another instrument recently reminded us how beautiful even our own planet can look when seen from orbit with fresh eyes. NASA's Earth Observatory has released a striking new image of the circular Richat structure in northwestern Africa, sometimes called the Eye of the Sahara. The formation's immense scale and almost perfect symmetry are only fully appreciated when viewed from space. From orbit, the eye-like pattern stands out so clearly against the surrounding desert that it's easy to understand why people once speculated it might be artificial. In reality, it is a deeply eroded geologic dome formed over hundreds of millions of years as layers of sedimentary rock were uplifted and then worn away by wind and water into concentric rings of different colors and textures. Satellite perspectives like this continue to reveal hidden geologic features we simply cannot appreciate from the ground, no matter how many times we walk across them. It's a lovely reminder that even after decades of continuous Earth observation from space, there are still surprises waiting in seemingly familiar places if we know how and where to look. Shifting from the surface of our planet to the organizations that operate above it, some significant changes are happening inside the U.S. Space Force. The service is reorganizing and fully integrating the Space Development Agency into its structure. The agency will lose its previous standalone status, but its well-known go-fast acquisition culture and sense of urgency are expected to continue inside a new portfolio-based organization. Officials have been careful to emphasize that speed and innovation remain top priorities, even as the two organizations combine. The move aims to streamline military space development, reduce duplication, and create clearer lines of responsibility while hopefully preserving the agility that has driven a lot of recent progress in satellite technology and rapid deployment. It will be really interesting to watch how this new structure actually affects the pace of programs once the dust settles. Organizational changes like this often end up having more long-term impact on what actually reaches orbit than we realize when the announcements first drop. While governments reorganize their space efforts, private industry is also steadily expanding its footprint on the ground. Blue Origin is moving through the early approval stages for a new launch complex at Vandenberg Space Force Base in California. The site would add important West Coast capability for launching into polar and sun-synchronous orbits that are currently in high demand. Having another reliable commercial option on the California coast would meaningfully strengthen the overall launch infrastructure available to both government and private customers alike. Polar orbits are especially crucial for Earth observation satellites and climate monitoring missions, so expanding dependable access to them matters for science and national interests. This announcement represents yet another step in the steady, almost quiet growth of commercial space capabilities across the United States. I'm genuinely curious to see how quickly this facility can move from early planning and environmental reviews to actual launches on the pad. Every new pad that comes online increases resilience and options for everyone. Speaking of partnerships and new capabilities, two countries just formalized a fresh alliance that caught my attention. Canada and South Korea have announced a new collaborative agreement focused on low Earth orbit satellite communications, remote sensing, and broader space exploration efforts. Both nations bring complementary strengths. Canada's long heritage in robotics, radar, and communications payloads paired with South Korea's growing expertise in launch vehicles, satellites, and Earth observation. These kinds of partnerships outside the traditional big players are encouraging because they often lead to creative solutions and innovations that benefit everyone involved. Cooperation at this level can accelerate joint missions and technology development in ways that might not happen if either country worked alone. I'll definitely be watching over the coming years to see what concrete projects and perhaps even joint missions emerge from this new alliance. It's a reminder that space has always been at its best when different perspectives and capabilities come together. From national partnerships to the next generation of hands-on training, a university project just completed an important milestone. Purdue University has added the final members to its student-led space mission crew, continuing a long and impressive tradition of universities playing a direct role in real aerospace hardware development. These students are gaining rare end-to-end mission experience, from early concept and design through building, testing, integration, launch operations, and eventual data analysis that most young professionals only dream of at that stage in their careers. Programs like this are precisely where tomorrow's engineers, project managers, and mission leaders get their start and learn how to turn ambitious ideas into working spacecraft. It is always heartening to see universities keeping that talent pipeline strong, active, and deeply connected to actual flight hardware. The enthusiasm these students bring is infectious, and it makes me optimistic about the future workforce that will be building the missions we'll be talking about in the 2030s and beyond. Now, here's something that really caught my attention when I read the full technical details from the SPHEREx team. Beyond the beautiful big picture map of where these ices live, the mission is also giving us new insight into the exact chemical mixtures present in different environments across the galaxy. Some clouds appear surprisingly rich in carbon dioxide ice, while others show higher concentrations of water ice, and the ratios seem to tell a story about the temperature, density, and radiation environment each cloud has experienced. That kind of granular information is exactly what modelers need to improve their simulations of how material flows from one stage of star and planet formation to the next. And it's the difference between having a blurry sketch of the chemistry and having a high-resolution photograph. The more I read about it, the more I appreciate how foundational this work really is. You know what has always fascinated me about the life cycle of stars? If you could somehow safely scoop up a single teaspoon of material from the core of a star that has just gone supernova, that tiny amount would weigh about as much as a mountain here on Earth. For millions of years, the outward pressure from nuclear fusion in its core perfectly balances the crushing inward force of gravity. But when the star finally runs out of fuel, it can fuse. That outward push suddenly vanishes and the core begins to collapse at a staggering fraction of the speed of light. Protons and electrons are forced together into neutrons, creating a neutron star that's roughly the size of a city yet contains more mass than our sun. The collapse is so violent that the outer layers of the star rebound off this newly formed ultra-dense core. That rebound, combined with a flood of neutrinos trying to escape, drives a shockwave outward that ultimately rips the star apart in a brilliant supernova explosion. The material ejected travels at thousands of kilometers per second and seeds the surrounding galaxy with the heavy elements we need for life, for technology, for planets like ours. Smaller stars like our sun never reach those extreme core densities. Instead, they swell into red giants, gently puff their outer atmospheres into space over thousands of years, and leave behind a white dwarf. We can watch these explosions across the universe and model the physics with powerful supercomputers. Yet one specific mystery remains: exactly how the neutrino-driven shockwave manages to revive and explode the star in every direction instead of stalling in some cases. That precise mechanism still keeps astrophysicists awake at night. It's one of those beautiful scientific problems where every answer seems to uncover three new questions. The more we learn, the more we realize how much remains to discover. That's what keeps me coming back to this stuff. Before we wrap up today, keep an eye on how those nuclear propulsion concepts we discussed earlier move from proposals into actual test hardware in the coming months. It feels like momentum is building. That covers the major space and science stories that caught my attention this week. If you enjoyed any part of it, please share the episode with a fellow space enthusiast. It really helps the show grow. I'm Patrick in Vancouver. Thanks for spending some time with me among the stars. See you tomorrow, Kia 478. This podcast is curated by Patrick, but generated using AI voice synthesis of my voice using ElevenLabs. The primary reason to do this is I unfortunately don't have the time to be consistent with generating all the content and wanted to focus on creating consistent and regular episodes for all the themes that I enjoy, and I hope others do as well.
Drifting softly through the black, a million stars behind our back, the void hung